You're watching a Channel 98 NBISD TV production.
Hello out there in TV land. Welcome to Deja Vu. It's Algebra 2. As always, I'm your mathematical host, Kevin Corpy. Today bringing you lesson 28. Now we're going to kind of start a section today, or a unit if you want to call it, that's going to carry over into several episodes. We're going to be talking about conic sections today. And we're going to be looking specifically at one type of conic section, and we're going to kind of hopefully finish up in about 3 episodes. Now conic sections are something that goes back a long time, or at least parts or certain conic sections do. And as you're going to see at the end of the show, if you stick around, and I hope you do, we're going to look at an example that goes all the way back to basically 3000 BC, prehistory essentially, before written history. And then we're going to talk a little bit about some of the Greek mathematicians still in early BC who had a profound impact on the development of conic sections. And if you stick around with me for 3 episodes, you'll be walking around your neighborhood, out in public, and you're not going to help but notice conic sections. So download the worksheets from the district website and stick around with me for 30 minutes a day and for the next couple of weeks to learn about conic sections. Guaranteed to be exciting. Lesson 28, conic sections and an introduction to the circle. All right. Now on past episodes we've studied a parabola, and as you're going to see, a parabola is a special type of conic section. But the parabolas we've seen on previous episodes have all been functions, which means that they've passed the vertical line test. Most of the conic sections that we look at on these next 3 episodes are not going to be functions. They're going to be curves, but they're not going to be functions. They're going to fail the vertical line test. In fact, most of them do, but that's okay. We can still discuss them. We can still talk about them. Now, what is this conic section? Well, a conic section is nothing more than a cross-section of a right circular cone. Well, here's what a cone looks like. And basically, we can slice this up any way. We could slice it horizontally, at an angle, vertically. And every time you do, you cross or take a cross-section of this cone, you get a different shape for your cross-section. And it will be one of the conic sections that we're going to be looking at. Here's another diagram of what we're essentially doing here. This is called a double-napped cone. It's a cone with another one on top of it. And that one is specifically needed for one specific type of conic. But notice we're dissecting or cutting it with a plane, kind of like slicing it with a knife. And each time we do, we're going to get a different cross-section. Now, conics have been around for a very long time. Certain type of conics have been discovered that date back to prehistoric times in 3000 BC. But they were originally studied, as far as we know, very intently by a Greek mathematician named Apollonius, who was a contemporary of Archimedes. There's a coin depicting Apollonius. Okay? He's actually the guy that gave the conics their names. Well, later on, another Greek mathematician, a rare female mathematician, they often go unnoticed, Hypatia, studied conics as well, spent a lot of time working with conics. Now, the Greeks were drawn to conics because they were beautiful, but they also served a very, very important practical purpose. Okay? And we're going to see some of the diverse practical purposes of conics as we go through the next few episodes. Okay? So let's take a look now at what the actual conics are. There's 4 types. Okay, the 4 types of conics that we're going to be primarily looking at are circles, ellipses, which is the correct mathematical name for an oval, hyperbolas, and of course the parabolas that I already mentioned. Those 4 right there. There are other types called degenerate conics, but they're really exceptional cases of these right here. Okay, so let's take a look at an equation of a conic and kind of see what it looks like. Here's an example right here. We want to sketch the following conic section. X squared plus y squared equals 25. Now in functions, it's okay to have x squared. But as soon as we introduce a y squared, that means that we're going to have 2 different values of y for one given value of x, which violates the function rule. So it's not a function, but it is an equation. Now, we want to sketch this on our calculator. So to do this, we need to explicitly solve this for y. And we're going to have 2 explicit functions. So what we'll do is we will solve for y by isolating it. So we will subtract x squared from both sides, and we will take the square root of both sides. Now, whenever we take the square root, we're introducing it to the problem. Remember, we have to extract the positive and the negative root. So we get plus or minus 25 minus x squared. Okay? Now, that's actually two equations. We get y equals positive 25 minus x squared, and then we get y equals negative square root of 25 minus x squared. And if you remember from the last episode, simply multiplying any function by negative out front is going to reflect that graph across the x-axis. So this should produce the top positive half of our conic, and this should produce the bottom half of our conic. Now the question is, which conic which conic is it? Let's go to the calculator and see if it can't draw it for us and see if we can't figure it out. So once we take our equation and we solve it explicitly for two separate functions of x, then we can graph each of those on the calculator, in y sub 1 and y sub 2. I'm going to show you how to do that right now. Turn your calculator on. That's a good place to start. You go to y equals and clear out whatever's there. Now you're going to want to type in the positive square root, or just square root of quantity, 25 minus x squared in y1. And in y2, you want to sketch the negative version of it. So your negative button is right here, square root of 25 minus x squared. And it's a good habit to close the parentheses. And then what you're going to do is hit zoom 6, which is a standard viewing window. If you notice what that looks like right there, it kind of looks like a circle, but it's kind of stretched. It looks more like an oval, an oblong circle. And that's because we're in a zoom 6 window, which puts more pixels on the x-axis. It's actually stretching it to fit the ratio here of vertical to horizontal. So what you want to do is actually, once you hit zoom 6, hit a zoom 5, which is your square viewing window. And what it does is it actually puts more pixels on the x-axis, but every pixel on the x and y-axis has the same length. And now you can kind of see something that looks more like a circle. Here's the top half, here's the bottom half. Now notice that it doesn't quite connect on the x-axis, and that's because your calculator is a function graphing machine, and it doesn't like to graph vertical lines, because vertical lines are not functions. In fact, they fail the vertical line test quite miserably. So anyway, solve it for two explicit functions. Type 1 into y1, the negative into y2, graph it, and you got it. So we actually have a circle in this equation. So yeah, it was a circle, okay? And you're going to get really used to recognizing the equations of circles. Okay? You're going to spot the equation and say, that's a circle. You're not going to have to graph it. Now the circle of all the conics is probably the one that you see most often in everyday life. There's many uses for the circle, from gears, tires, basically you can look around you and see circles everywhere. Okay? But there is a specific definition of a circle, and we want to look at how we actually obtain that from a cone. How do you get a circle from a cone? Well, if you take the cone, here's the cone, and you slice that cone parallel to the base. Okay? You slice it off. The cross section that you get right here is in fact a circle. Okay? And this picture right here depicts the same thing. The cross section is a circle. So that's how you get it from a cone. Now what's this precise definition I was talking about? Well, every conic section that we're going to be discussing has a precise locus definition. Locus, L-O-C-U-S. And all a locus is it refers to an area or a region, or in this case, a set of all points. So here's the precise mathematical definition of the circle right here. The circle is a set of all points, or it is the set of all points that are a fixed distance, which we'll call R, from a fixed point, which we'll call C. Okay? All the points that are a prescribed or fixed distance from a fixed point. Now, that fixed distance we call R, that's going to end up being the radius of the circle, and the fixed point, C, is going to end up being the center. And we're going to go ahead and give, by convention, the coordinates of the center to be at h, comma, k. The x-coordinate of the center is h, the y-coordinate is k. Okay? Here's a little diagram of what I was talking about. Here's my fixed point, hk. If I prescribe some distance r, okay, this could be a point that's r units away. Imagine getting a string, anchoring it down here, and the string length is r. And then you can swing it all the way around, and every single point that lies on the perimeter or the circumference of the circle is going to be the same distance from that center right there. Okay? And that's r. Now, what we want to do is somehow take this idea, this definition, and we want to establish an equation based on it. So I'm going to derive the equation of the circle for you right here, because it's going to tie into something that we've been talking about all year. Here we go. Here's my point, HK, right there. And then here's my point, XY. So this is my fixed point. This is a point that lies on the circle. Well, what we're going to do is we want to find the distance between them, and I'm going to call that R. So what I can do is I could just kind of connect these lines here, drop a perpendicular and run a horizontal, and create a right triangle. And once we have a right triangle, we can use Pythagorean theorem. Well, the length of that vertical side is going to be the change in the y values. If this y value is y and this y value is k, then this side length right here is y minus k, top minus bottom. What is the length of that little leg? Well, that's just the change in the x values, which is going to be x minus h. So now I have the side lengths, the two short side lengths, and I have the hypotenuse. By the Pythagorean theorem, we get this. We get x minus h, the horizontal side length, squared, plus the vertical side length, y minus k squared, is equal to the hypotenuse, which is r squared. And this right here, believe it or not, is what we call the standard form for the equation of a circle that has a center at the point HK and a radius of r. So a circle's definition by way of the Pythagorean theorem gives us the standard form equation. And that is something that you're going to be able to recognize. We got a squared term for the x, a squared term for the y, and our radius is isolated on the other side, which is just a number. And the square root of that number is the radius. Now, writing equations of circles is a very important skill that you need to practice to get good at. So let's go ahead and try that now that we have our standard form of the equation. So here's a nice example. We want to write the equation of a circle that's centered at the point negative 2, 5, that has a diameter of 16. Okay, equation of a circle. Well, what we can do as soon as we see that is we can kind of write out the standard form. X minus h squared plus y minus k squared, quantity squared that is, equals r squared. So what essentially do we need to get our equation of the circle? Well, we want it to be an equation of x and y. So we need h and k, which is the center, and we need the radius. That's all we need. We need the center, we need the radius. Well, here we go. It's given us the center. So h is negative 2, k is 5. I can drop those right in. Do I have the radius? Well, not explicitly. We are given the diameter. So if we have the diameter is this 16, how can we find the radius? It's half of it, right? So the radius would be half of 16, or 8. Now, it's very important to read the questions carefully and not just jump in and take the numbers that are given and plug them into the equation. Because every once in a while, you might have to go fishing for the value that you actually want. But you should be given enough information to find those values. In this case, the diameter was a real quick, easy thing that led us to the radius. Now I'll carefully plug in. It's x minus h, which is negative 2 squared, plus y minus k, which is the y-coordinate to the center, 5 squared, equals r squared, which is 8 squared. Now we'll just simplify just for aesthetics here. Minus a negative is really plus. I get x plus 2 squared plus y minus 5 squared equals 64. And there you go. That is the standard equation of a circle centered at negative 2, 5 with a radius of 8. Let's quickly see how we could sketch that. The way you sketch that is you want to plot your center. Your center is going to be at negative 2, positive 5. So I'm going to use more of the quadrants 2 and 3. There's negative 2, 1, 2, 3, 4, 5. Right there. There's our center. Now, you can actually draw some points on the circle and connect the dots. The easiest points to get are the ones that are vertically aligned with the center and the ones that are horizontally aligned from the center. The ones at the diagonal are a little bit harder to draw. So if we just count 8 units in all directions, vertically and horizontally, we get some points. So 1, 2, 3, 4, 5, 6, 7, 8. We're going to be up there. This is going to be back down 5. So 6, 7, 8, 3 more puts me there. So those are the 2 points, 8 units above and below. And then to the right, that's 1, 2, 3, 4, 5, 6, 7, 8 over here. And then 1, 2, 3, 4, 5, 6, 7, 8. So it's a lot of counting. But you get those points right there. And the way you connect them is with a arc. And you gently draw your circle. And there you go. There's your sketch. It doesn't quite look like a circle, but with a little imagination, it surely does. And with a little practice, you don't have to imagine so hard. Okay, let's take a look at another example. In this case, we want to write the equation of a conic whose points are all equidistant from the point -411 that passes through the point 5, -1. So in this case, they're telling us it's a conic. They didn't tell us it was a circle. How do we know it's a circle? Whose points are all the same distance from a fixed point, -411. Ah, I remember the definition. That's the circle. So the fixed point, -411, is my center. So this is my HK. H is -4, and we have K is 11. But I don't have the radius in this case. I have a point through which it passes. Well, let's come back up here. If I know H and I know K, but I don't know R, then I need to know an X and Y that pass through the circle so that I can find R. Well, it's essentially what we have here. Or you can go back and derive the equation in the exact same fashion I did when I derived the equation. Well, let's go ahead and drop it into our equation. So once again, we write it, x minus h squared plus y minus k squared equals r squared. And I would recommend writing that every single time, because the more you write the template, the standard form, the more it's going to sink in. Now we'll carefully drop in our values. We have our x value, which is going to be 5, and the y value is -1. That's what it passes through. So we get 5 minus -4 squared plus -1 is my y value minus k, which is 11 squared, and that equals r squared. I don't know what r squared is. Now I evaluate. That's going to be 9 squared plus -12 quantity squared equals r squared. Well, we get 81 plus 144, which equals r squared. And if we add those together, we get 225 is r squared. Now, really, we only need r squared, remember, for the equation. We plug that right in. But it's always nice to know what the radius is. The radius is the square root of 225. And in this case, it's positive, because radii are only positive, which gives us the fantastic number of 15. So the radius is 15. The center is at -411. I'm not going to draw that one, because that's going to be a very large circle. But let's go ahead and write our equation then. We're going to put it back in terms of x and y. So x plus 4 squared minus -4 plus y minus 11 quantity squared equals r squared, which was 15 squared, or 225. And there you go. So a little bit different information given to us, but still enough to write the equation. A couple of extra steps. Takes a little practice, but you do enough problems, and just like anything else, you get good at it. All right, time for a real quick public service announcement. Don't go away. We're going to be right back. While you're gone, though, think about this. What do lazy dogs do for fun? The answer when we return.
When you give up the ability to decide for yourself, you give up what makes you, you.
Welcome back to Deja Vu. It's Algebra 2. I'm your host, Kevin Corpy, talking to you today about conic sections, circles in particular. Did you figure out what lazy dogs do for fun? Well, they don't do math. What they do, though, is they chase parked cars. Okay, let's get back to circles. Now we're going to look at a very important piece that's related to a circle, and it's called a tangent line. If you remember from geometry, a tangent line is basically a line that touches any curve in exactly one spot. In this case, we're talking about the curve that is the circle. So I have drawn in a tangent line right here. It basically comes in from space and right there, just kisses the circle at one spot and keeps going. Now, if you also remember from geometry, any tangent line is perpendicular to the radius at the point of tangency. Okay? So one other thing that you're going to have to do besides writing equations of circles is to write an equation of the tangent line at a given point of tangency. And we're going to do that right now. Here we go. We want to write the equation of the line that is tangent to the circle x squared plus y squared equals 29 at the point 2, 5. Let's go ahead and see if we could draw this. X squared plus y squared. That's like x minus 0 squared plus y minus 0 squared. So that implies that the center is at the origin, 0, 0. Our radius is the square root of 29, which you know without a calculator is between which two integers? 5 point something. That's about all we need to know. So let's go ahead and draw that. Here's 0, 0. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and point something. There you go. What I did is I just sketched it in there, something reasonable that's going to allow me to draw on. Well, now the point of tangency is the point 2, 5. So that's 2, 5. It's right there. Okay? So if you want to draw that tangent line, I'm going to come over here and turn my paper. You draw it, and it has to come and touch right at that one spot, and then it keeps going. All right? So they intersect right there at one point only. We want to find the equation of that line. How are we going to do that? Well, remember, for the equation of a line, we use the point-slope formula. Y minus y sub 1 equals m times x minus x sub 1. Another thing you should have up here in your noggin. Well, we need the slope and a point. We have the point. The point of tangency is 2, 5. So we have our x sub 1, y sub 1. We just need the slope. How do we find the slope? Well, remember what I said. The tangent line is perpendicular to the radius at that point. If I could find the slope of this radial line, then remember from algebra, from geometry and algebra, got to remember everything, right? That perpendicular slopes are opposite or negative reciprocals of each other. So that's my plan of action. Well, how do we find the slope of the radius? Well, the center is at 0, 0, and the point of tangency is 2, 5. So it's the change in y's, so that's 5 minus 0, or 5, over the change in the x values, which is 2 minus 0, which is 2. So the slope is 5. From the center, we go up 5 over 2 to get here. So that's the slope of the radial line. So my perpendicular slope, which I'll write as m subscript perpendicular, is negative 2/5. Now we have the slope of the tangent line to be negative 2/5, and we have the point 2,5 through which it must pass. So now we carefully plug into the point slope formula. Here we go. We get y minus 5 equals negative 2/5 times x minus 2. Now that right there is technically an equation of a line, so you could stop there. If your teacher prefers you to get it in slope-intercept form, we're running out of time, so I won't actually go through the calculations, but you just expand it and collect your like terms on one side, and you get plus 29/5. Negative 2/5 x plus 29/5, and now you can see the y-intercept. So ask your teacher which form she prefers eventually, but we can still use the point slope formula to get it set up. Now it's time for Deja Review. Oh yeah. All right, today on Deja Review we get a little historical treat. We're going to be talking about Stonehenge. Now if you're fortunate enough to have actually been there and visited the site, I hear it's pretty impressive. I haven't been myself. But it's an ancient prehistoric monument that people are still puzzled about. It actually contained originally a large outer ring that's not shown here that was originally built of just mounds of dirt. And that was about 3000 BC. Then about 2000 BC, the second phase of construction kicked in, and that's when this inner ring was built. And that inner ring is called the Sarsen Circle. Now, in England, if you go there and see, you'll see pieces of the Sarsen Circle that are still standing. Okay, it's dilapidated and some of the stones are missing, but that's pretty much the inner ring, which most people kind of associate now with the monument itself. But it did have this larger outer ring. Okay, it's a circle, okay, and it's remarkably close to a perfect circle, which on such a large scale, 3000 BC, is pretty phenomenal. Now we're going to look at some calculations that involve this circle. Whether the ancients, prehistoric people that built this actually used the calculations, we don't know, but they certainly knew something about circles. Okay, so let's say that the outer ring of Stonehenge, which again is not shown, it would be this one here, can be modeled by this circular equation. X squared plus y squared is 27,225. So remember, this is the radius squared. That's really 165 squared. So what we're doing now, essentially, by writing an equation, is we are superimposing a coordinate grid over Stonehenge. Okay? And we're saying that the outer ring then existed 165, we're going to be in feet, from the center of this inner circle. So it was 165 out. The other one, the Sarsen Circle, the inner ring, can be modeled by x squared plus y squared equals 2916, which is the same thing as 54 squared. Okay, so the diameter is 108 feet all the way across this inner ring, and the radius is 54. Okay, here's some questions. We want to discuss something called the heel stone. The heel stone is another important stone that's been named over there, and it's located outside of the circles, even outside the larger circle. And it's approximately at the point 0,300, which is going to be from here, we go up 300 units, which is going to be off my page. Okay, but it's a single stone that just stands on the outside. It did have some significance, and you can research this to kind of see what the significance was. But be careful, the more you research, the more time you're going to spend researching because it's very intriguing. What we want to do is we want to find the maximum and minimum distances in feet from the heel stone to the outer and inner rim. Okay? And to do that, I'm going to actually draw a little bit larger diagram. So here we go. Here's the center of Stonehenge. Here's the inner ring. Here's the outer ring. And here is the heel stone. Okay? Here's my x-axis. Here's my y-axis. We already established that the radius of the inner circle was 54. It was the square root in the equation. And the radius of the outer circle ended up being 165. The heel stone, it was at the point 0,300. That means we had to go up 300. That means this distance here is 300. So we have all these little images here. Now, what we want to do is figure out what the minimum distance is, which would be that, and the maximum distance to here. So let's go ahead and do that. Let's just do it for the outer ring, and you can figure out what the inner ring is kind of by the same method. So let's call this x, and let's call this y. We want to figure out what x and y are. Well, let's go ahead and figure out what x is first. Okay? How do we find x? If we know that the total distance from the center to the heel stone is 300, and the radius of the outer circle is 165, then x should be the difference between them, 300 minus 165, and that's going to give you 135, if I'm right. Yeah, 135 feet, right there. Okay? So from the outer ring to the heel stone is still another 135 feet. I mean, that heel stone is way out there. Now, what's the maximum distance from the heel stone all the way to the outer edge on the other side? Well, it's going to be the minimum distance right here, 135, plus all the way across, which is the diameter of the outer circle. So we need the radius, and we have to double it. So here we go. Y, the maximum distance, is 135 plus 2 times the radius, which is 165. And if you calculate that out, you get to the outer ring, the maximum distance is 465 feet. Okay, so there you go. You do the same thing for the inner circle, and you can figure out the maximum minimum distances. But notice it required us to know what the radii were of the inner and outer circle, which we conveniently got from the standard form of the equation on the circles. Okay, now we're about out of time, and you know what? I think I'm going to try and plan a trip to go see this in real life, because just talking about it to you on TV, I'm getting pretty darn intrigued. So we'll see if I can't schedule a little trip there. So there you go, lesson 28 in the can, all done. Now, got Stonehenge right here behind me. I traveled all the way to England just to do one little finishing shot, but you know it's worth it. This is just one of the prehistoric marvels of the world. How did they get those giant stones to the very top? And how did they get all that to lay out perfectly in a circular configuration? Well, unfortunately, the outer ring is no longer standing today, but we still have a great monument that remains from prehistoric times, 3000 BC, a lasting tribute to a conic section, the circle. So we're out of time today. I'm going to go over here and see if I can investigate these stones a little more closely. I hope you'll join me next time, though, as we look at another conic section on Deja Vu, it's Algebra 2. Until then, though, I'm your host, Kevin Corpy, reminding you to do your homework and don't climb on the stones.